Right. Hey guys, my name is Sreyan Ghosh, and I'm going to be talking about deep learning today. So, a bit about myself. I'm a first year undergrad student at VIT University Vellore, and I'm passionate about deep learning, machine learning, artificial intelligence, and all the shebang associated with it. Right now, I'm also doing a bit of blockchain. But my primary interest lies in deep learning. So, I'm going to be talking about deep learning a bit. I'm going to be going through the mathematics of it, not in depth, but just so that you can understand why deep learning is such a powerful tool today. So, I would like to ask you, how many of you already know what deep learning is? And please write your answers in the comment section. So I want this session to be as interactive as possible, so that I can resolve your doubts whenever you have them. And if you want me to go deeper into a topic, I surely will if the time permits. So does anyone know what deep learning is, or has a clue, or where it's being used, how it can be used? Anyone? So I'll be waiting for a reply for about 5 seconds or so. So if none turn up, then I'm just gonna proceed. So anyone want to say what deep learning is, or what the potential of deep learning is, what it does? No? Fine. So deep learning is basically, we've all known this system of functions, right? Y is equal to f of x. Hi Mansi. So you know what deep learning is? So you want to tell us something about it? What deep learning is and what do you think it is? Alright, neural networks, forward propagation, backward propagation. Indeed, it is the same thing. It's that. There's a lag, I see. Alright, fine, we'll continue just like that. Not pay much heed to it. Yeah. Alright. Cool. So, neural networks, yes, deep learning is neural networks. Forward propagation, yes, backward propagation. Actually, these are techniques that constitute what deep learning is all about. But deep learning is, in its essence, a function estimator. Like, as I was saying, you have a function, right? Y is equal to f of x. So, if you're given two of these parameters, somewhat like you have been given x and you have been given an f. So y is equal to sine of x, for that matter. If you're given some x like 1, 2, pi by 2, whatever it is, you can easily compute what y is going to be, right? That's simple. And the other way around, if you're given some y, and let's talk about the same case, y is equal to sine of x is the sine inverse of y. Well, if you did guess that, well, you passed class 10. Fine. I'm trying to make this interactive and all. Just don't go for my lame jokes. But whatever. So x is equal to sine inverse of x. We can easily compute x from the sine inverse of y thing that we have. But suppose we're given an x and a y. Do you think we can compute f that easily? Like your views on that? We're given an x and a y. Can we find out f? Guys, there's a lot of lag actually. Still wait a second because I have not yet finished with it in the video. Alright, since we're not getting any answer, so we'll proceed because we're in a time crunch of sorts. So never mind. Yeah. Moving forward. Yeah. So let's go on. To answer the question that I had put forward, if we're given one y and one x, it's nearly impossible for us to find out what f is. I mean, what can be the estimator that equates both these things, right? That's not easy to find out from one example. But what if we had a large number of such examples, what we call a data set, right, or a data frame? If we have such a data set or a data frame, it is quite easy to understand. Not easy, I'll not say easy, but it's quite possible that we might figure out what this function is. And right now we're talking about something which is, either one-dimensional or two-dimensional, but complex data of multiple dimensions, n-dimensional data, that also can be estimated using deep learning. Right. So that actually is the power behind deep learning. We can find out the facial recognition, natural language processing. These are actually very interesting and intriguing terms in deep learning that we often associate with deep learning. But behind all of this is a very simple concept of mathematics running, which has to be run a lot of times. We have to iterate over this simple mathematics a lot of times, but we get a very satisfactory result in the end. I mean, we can solve a lot of problems using deep learning, which is why it is now a hype, right? Everyone wants to know what deep learning, machine learning, data science, it's all about, right? So moving forward, why deep learning and why now, right? So deep learning, like, I need not tell you about its potentials, right? Because frankly, if you needed to catch a terrorist at an airport, and humans might falter, but a deep learning algorithm and in a CCTV camera will not. It will let you identify the terrorist at the airport, and your legal troubles, your national security, it's solved. So right now, this picture, the slide that you're seeing here right now, it's something known as a convolutional neural network's feature extraction. Different steps of feature extraction in a convolutional neural network. My face might be covering it up a bit. So this is what a convolutional neural network does in step one. For those of you who don't understand what a convolutional neural network is, or are not at the same step with me, well, it's basically a type of a neural network which lets you make determine results on images and videos and that sort of thing, right? So what a CNN is doing here in this first place is it's extracting low-level features. We'll get to the depth of all this in the detail later on. So it's extracting the low-level features first, which are the lines and edges. I mean, if you look at my face right now, what a convolutional neural network will do while seeing at the same image is it'll find out the edges of my face, right? It'll find out where my face ends, where my beard starts, where my beard ends, the contour of my nose, in a very sketchy, in a very rough manner. This will happen in the first stages of the neural network. Then, as we move forward in the neural network, in the next layers, it will extract the mid-level features, where my eye is in my face, where my nose is, how long my nose is, right? How much my hair is in density or something like that. Right now it's a lot because of the lockdown. I've not been to the barber in about 2 months, so forgive me for that. And the last layer is what extracts the entire facial feature of that person, right? I mean to say what the entire face might look like to the neural network. So that's how it might classify between different people. It might classify between a person who's a man or a woman. It might even, nowadays we have advanced software which can even predict the age of a person to a considerable amount of accuracy. And that's all done using convolutional neural networks. So we'll get into the depths of CNNs later. It's a bit complex to look at, but we'll start from the very basics so that everyone understands what's going on behind the scenes. So now we come to the question, why now? I mean, convolutional neural network itself existed long back. I mean, the first convolutional neural network was known as a LayNet. It was made by Jan LeCun in the 98, if I'm not wrong. Right, it was a 5-layer network, and it really was a breakthrough. But back then, we didn't have the processing power, nor did we have the data to compute or to create a model which can successfully identify faces. The facial recognition software came way later in the 2010s, 2011s or so, when you had the ImageNet challenge going on. Well, for those of you who don't know what the ImageNet challenge is, it is basically a challenge where a computer algorithm or a convolutional neural network, you might use whatever you want, but the network that won the ImageNet challenge, all the networks that won, they used to announce a winner every year. They were all convolutional neural networks. I mean, if you've heard that on computer vision, convolutional neural networks play a huge amount of role there. So right now, why now? It's because we have a lot of data. This big data is not similar to the big data analytics that you've heard. We have a lot of data. I mean, you can use big data to make conclusions or estimations in deep learning models. That's absolutely all right. So right now we have a lot of data. We have sophisticated hardware. We have graphics processing units, GPUs, which let us parallelize the operations that we run, these mathematics that we run behind the scenes. It helps us to run them at a very fast rate. And we have a lot of software, which make it easy. I mean, right now there's, I don't know if you've heard of it, there's something called AutoML by Google. All right. So if AutoML develops a lot, I don't think we'll need people as deep learning researchers or deep learning engineers or machine learning engineers anymore if AutoML succeeds a lot, because you don't have to do anything in AutoML. Like, just go there, put your data set, tell what you want, and that's it. Like, you'll get all the results that you need and all that. So talking about software, we have a lot of frameworks that enable us to practice deep learning. We have TensorFlow, we have PyTorch, we have Apache MXNet, to name a few. If you're interested in computer vision, MXNet has a very good, kind of a sub framework or an extensive library called Gluon CV. Just if you're interested in vision, then you should take a look at that. Moving forward, we'll start with the Perceptron, the very fundamental, the structural building block of deep learning. Before that, I would like to ask if anyone has any questions. If you need me to clarify anything at all, please tell. Do we have any questions? Any questions, guys? No questions? So I'll move on. So the perceptron. So what exactly is a perceptron? All right. Here we have Mansi saying that forward propagation. Right, I'll explain forward propagation while explaining the perceptron. So the perceptron is an architecture of sorts which enable us to understand what this f factor in y is equal to fx is. Right? It rather is a predictor of sorts. I'll explain the structure of a perceptron to make you understand how crucial a role it plays. A perceptron as such cannot do much help in computations of complex tasks like facial recognition, but it is the building block of a deep neural network. So in a perceptron, if you look at my cursor here, we have inputs, right? We have inputs x1, x2 up till xm, and what we do is we take a weighted sum. A weighted sum is when we multiply the inputs with some weights. We'll talk about the weights later. Excuse me. We take a weighted sum and we apply a sort of a non-linearity to it to obtain a predicted value. Right? So we are given an x and a y. Our job is to compute the f. So we have a lot of x's, sorry, x1, x2 up till xm, and all of these are going to give me some y. So now my job is to compute this y and compare it with the y's that I already have, the actual outputs. And the outputs that I have, I'm going to compute something known as a loss, using something known as a loss function. We'll get to everything in detail later. I'm just explaining this. This loss that we calculate, we try to upgrade or update our network using these losses. We'll send the losses back throughout the network, what is known as back propagation. We'll back propagate these losses, these actual error correction terms that we have, and we'll update our values. We'll update the weights that we have. So that is basically what the principle behind the perceptron is, to find out a y hat or a y pred which is as close to the actual y that we have. So we have the inputs, the x's, the weights. Every single input has a weight associated with it. We take the weighted sum at this step. We apply a non-linearity, a non-linear activation function. We'll get into what an activation function is later on as well. And of course, we have a y hat, which is the predicted output, the y pred. Right. So at every step, as I said, a single perceptron or a single neuron as such, we tell this to be a neuron, can't do complex calculations, can't be of much help to us. So what we do is we take a lot of them and we associate something known as a bias term to these functions. Alright. So what do these bias terms do? It gives your neuron a sense of uniqueness. Right? It is an extra term that we need to understand or update during our back propagation, so that every single neuron that we have has certain unique roles in understanding what the output might be. If it seems sketchy right now, forgive me, but as I explain the mathematics behind it, I hope it starts getting clearer. And if you have any doubts at any step, please feel free to mention them in the comments. So here we see an addition of a bias term, right? The W0. So over here in the equation as well, you can see the bias term. Nothing has changed from the above equation, just a bias term has been added, and then we apply non-linearity to it and we get the output. So now we come to something known as the forward propagation in the matrix sort of sense. Over here it was all, very, what do you call this, algebraic or very individual term wise, but over here we're going to be dealing with matrices rather. Or if you look at this equation, it's the same thing as the above equation, which has been grayed out. In the matrix form, in its vectorial representation, we're just taking a dot product of the x vector and the w vector, which is basically the input and the weight vector, and we're getting the y pred. It's the same thing written in a fancy manner, so don't get scared looking at this. Alright, so now we come to activation functions, right? So activation functions are basically non-linearities. So why do we need non-linearities? Like, our activation function could have been anything. Like, we could have done a y hat is equal to mx plus c, where m is a linear term. But we're putting a g, which is a non-linearity. Over here, we've included the sigmoid function, which looks like this, and graphically it is something like this. We have a lot of other activation functions as well. We have our sigmoid function, we have our tan h function, or the hyperbolic tangent, or the tan inverse function. Then we have our ReLU, or rectified linear unit. We'll get to it, what ReLU is. We also have something known as leaky ReLU. We'll get to every single part of this, where each activation function is used, why should we use one over the other, or what are the advantages or disadvantages at different scenarios and all that. So moving on, we have, as I said, sigmoid, hyperbolic tangent, ReLU, rectified linear unit. So the importance of activation functions. The purpose of activation functions is to introduce non-linearities. If you look at the data that's given here, you can't really segregate the red points from the green points using a linear function, right? Can you? Like, let's move forward and see. This is what you can do. I mean, if you know of something known as linear regression, then this is the maximum that you can classify or separate the data using linear regression. So these are not that accurate. I mean, you look at the red portion of the data, the thing that's shaded red, you have a lot of green points. It's not properly segregated, is it? But if you start introducing non-linearities inside, this is what you get. Not perfect, you still have little red dots encroaching in the green dot area, but it's acceptable, right? We're obtaining what we want. The result that we're obtaining is quite similar to the actual result that we have. So that's why we have non-linearities. That's why we have the G, which is non-linear in nature. So over here we have an example. We have introduced certain random weights and biases, and we find out what the y predict is supposed to be. So if you move forward, this is the line. The matrices, the x1, x2 is multiplied with 3 and minus 2 respectively, and the bias term is added to obtain this line. So now if we have any given x1 and x2, we can easily compute our y hat term. So over here they've taken the x1 and x2 as minus 1 and 2 respectively, and obtained nearly 0.002 as the y pred. Over here you might be wondering how they got from this g of minus 6 to 0.002. Well, the g they've applied here is the sigmoid. You can just put the g in 1 by 1 plus e to the power minus x, and you'll get the same result. So this is what an example of a perceptron is. A single perceptron. Well, it's doing a fairly good job at classifying data. Now we'll move on to understand how to build neural networks with perceptrons, or something known as multi-layer perceptrons, right? So over here we have a single perceptron giving us a single output. Right, this is taking it even simpler. We have a bias, a W0, and an XJ, WJ, the inputs and the weights, weighted sum of that, you obtain the Z. So now, what if the output that we get, we feed this to another layer of perceptrons, right? Because if we have two outputs of such like Z1 and Z2, and all of them are connected, that's why we call it dense connections. Like every single input is connected to what we call this as a output layer in this scenario. It's connected, and applying a non-linearity on this Z1 that we get from X1 after taking the weighted sum, that is a predicted Y1, right? Now what if we take this Z1 and Z2 and feed it into another layer, considering these as inputs? This is basically the code, right? That we have. For the code, I'll not be discussing the code here though, because it'll take up a lot of time. But if you want to know what the actual code looks like, or what a code for the convolutional neural networks are, for recurrent neural networks are, for those of you who don't know what those are, we'll get to it, I promise. But for those of you who don't know what those are, I'll be putting my GitHub link there. It has extensive work on PyTorch and TensorFlow, so you can go there and look at all the code. It's quite easy in a sense, because I've not used much complicated code. It's pretty simple. I was learning myself, so I wanted it to be as simple as possible. So over here we have the multi-output perceptron, where we're getting two outputs. In the previous scenario we had seen one output, one y hat. We have y1 hat and y2 hat over here. So this is a dense connection. In TensorFlow we have that as tf.keras.layers.dense with units 2. Since we have two output layers here, we have 2 as units there. In case you're wondering what Keras is a library inside of TensorFlow framework, which is really helpful in performing deep learning tasks. So now we have a single layer neural network. So these are our inputs. This is what we call a hidden layer, or intermediate layer if you might call it. And this is what the output layer is. You might ask, why are we doing this? Like, what is the need for introducing a hidden layer? Well, a pretty simple answer would be to increase the accuracy or the prediction rate. That is why we introduce not one, but multiple hidden layers. If you look at convolutional neural networks, you will find a lot of hidden layers in them. I was speaking about the ImageNet challenge. The last convolutional neural network had around 150 of these hidden layers. So that's quite a complicated network. Training that would be a mess. So thankfully we have GPUs now, as I talked about earlier. So that simplifies the process somewhat. Now, this is basically the mathematics behind a single layer neural network. We're looking at Z2 over here. So what we're doing is, on a very rough note, we're taking X1, we're multiplying W1, 2 to it, the weight associated with this hidden layer component, and we're computing Z2 from this, right? So when we get the Z2, we're again going to propagate the Z2 forward, or the forward propagation, along with the outputs we have from Z1, Z3, Z up to Zn. And we're going to find out what Y1 hat is, and similarly what Y2 hat is. So this is the code for a multi-output perceptron. I mean, you can see we have two dense layers here, this being one of the dense layers and this another one of them. Follow my cursor if you can't understand. This is the first one and this the second one. So we're looking at tf.keras.layers.dense of n numbers of hidden layers, hidden units, like n units of them. So this layer tells us that there are n units, and this one tells us that we have two outputs. So you must remember this thing while doing any operation of such, that the last layer that you have, the last dense layer that you give, the outputs must be equal to what you want to do with what your business problem essentially is. Let me elucidate by giving you an example. Suppose you want to do a binary classification, right? So 2 neurons is sufficient for that. I mean, one will tell what is the probability of you getting the input data being of type y1, and this one will tell you the probability that it's y2. Or a special thing about binary classification is that you might not even, this is just the case of binary classification, mind you. You don't need even 2 for binary classification. 1 would suffice, because whatever you have for, say, y1, say you're getting a probability of 0.6 in that scenario, your y2's output is going to be 1 minus 0.6, obviously, which is 0.4. So if you are getting a very low value for your output, something like 0.2, you can safely assume it to be that it is of class y2. So this is a special case for binary classification. One output neuron does it. But in all other cases, the number of output classes you have, the same number of units we have in our last layer. Moving forward, this is a deep neural network with lots of layers. I mean, as I told you, the last convolutional neural network that won the ImageNet challenge, it had about 150 layers. So you can guess what scale the calculations go on in. Moving forward, applying neural networks. I mean, we're going to get an output, right? From that output, how do you think that we can, like, that output might not be the same as our intended output, right? Say we're going to get a value of, say, 0.2 in our first run, but what the neural network, what the actual output is say 0.6. We have a difference of 0.4, which is not something that's acceptable. So what do we do? As I said before, we apply this loss function and calculate the loss that we have. By what margin is our model faltering? I mean, what is the error that we have? So moving forward, actually I took this slide off MIT Introduction to Deep Learning. So they have all this funny anecdotes. So I'll just skip these since this is not a class as of now. Yeah, quantifying loss. Right. The loss of our network measures the cost incurred from incorrect predictions. Right. So over here, the predicted value was 0.1, whereas the actual one is 1. Like, there's a difference of 0.9. That's actually not acceptable at all. Like, if you were to say something that this is, classify something as a cat or a dog, if it's a cat, this would definitely classify this as a dog. I mean, poor example, but you get what I'm trying to say. So if you look at this complicated looking equation here, what we basically have is the f of the inputs and the weight. I mean, whatever our y pred is, this entire thing can be substituted by y1 hat, and this is the y1 actual. It's saying yi here. If we take one output in this case, we have y1. So y1, the loss between the y1 hat and the y1, that's taken out. And then what we do is quite interesting, if I might say. We compute the empirical loss, right, which is basically the total loss over the entire data set that we have. So for this, for a set of inputs, our fx predicted is 0.1, whereas the actual result is 1. It predicted 0.8, but the actual result is 0. We predicted 0.6 and the actual result was 1, so if you round off, it really gives us a 1. But that all depends on our rounding off criteria. I might not want it to be rounded off from 0.5. I might just want it to be rounded off from 0.6. But we'll get into what the criteria we set. But over here, it's intuitive that 0.6 will be rounded off to 1. So that's in fact a correct prediction. So this is the kind of loss that we have, a binary cross entropy loss. We have a lot of things that we might need to discuss about cross entropy loss. There's scale divergence that you need to understand for cross entropy loss. There's a lot of mathematics behind it, but for now, I would just like to run you through this very complicated looking equation. Rather, I'll just give you a very simple form of, cross entropy loss as I understand it. It's cross entropy loss. I have made extensive notes on this. So yeah, so basically what cross entropy loss is, it is the negative of the log of the prediction if our prediction is 1. Like we're talking about binary cross entropy loss, so let's assume that our output can be either 1 or 0, right? So if it's 1, the loss function is computed as the negative log likelihood of y pred, and if it's 0, then is the negative log likelihood of 1 minus y pred. So if you're not understanding this, it's perfectly fine. You don't actually, to compute deep neural networks, you don't need to understand what cross entropy loss is at this depth. You just need to understand the different types of cross entropy losses. There's categorical cross entropy loss, there's binary cross entropy loss, and there's something called a sparse categorical cross entropy loss. If you understand these things, that's well and fine. So from the name, you can understand that binary cross entropy is for 2 classes, when you have 2 classes. Categorical is when you have multiple classes. And sparse categorical, I'll have to explain a lot of math for that. So you can just go through my GitHub notes and you can understand what sparse categorical is if you're interested, but it'll take a lot of time, so I'm not doing it. I'm not even reached halfway yet, so just be going through. Then we have the mean squared error loss. This I think most of you are familiar with. I mean, you have the root mean squared error that all of us talk about in our statistics classes. So mean squared error is the same thing without the root. Moving forward, and over here you have, how in which place in TensorFlow it's stored, the mean squared error loss, but you don't need it as such. It's quite simple. You can just hard code it yourself. So now we get to the part of training neural networks, right? So now we have the loss. So what do we do with the loss? Well, we propagate it backwards and we try to update our system parameters such that we achieve the lowest loss, right? So we want to find the network weights that achieve the lowest loss. So what are we doing here? Let's just skip the equation as such. It'll take a lot of time to explain that. What we basically are trying to do here is update the weights in such a way that we get a y pred on which computing the loss function gives us a value of 0 or epsilon, where epsilon is a very low loss, or epsilon is something that we set. It is, the satisfactory level at which we are satisfied. Like, wow, how did I come up with that? It is the level at which we are satisfied, the minimum value, right? And it is basically something which tends to 0, obviously. Like, no one wants a high loss in their thing. A larger loss means poor performing model. So our loss function is a function of the network weights, of course. Like we're trying to calculate what the minimum weight is, what the optimum weight is, so that we get the minimum loss. So it's obviously a function of our network weights. So we initialize the weights. We'll get into what are the best practices of initializing weights later. There are quite a few initializing techniques, and there are quite a few loss functions or loss optimizing methods that we can discuss, and we will, I promise you. So we initialize them at a random point, and then we compute their gradient, or what is it? This what you see is a partial derivative of the j of w, which is basically the computed loss function, and we're taking its derivative with respect to the weight. So this is for the optimization of weights, and we'll take the derivative with respect to the bias when we are going to do the optimization of the biases. So we compute the gradient, and what we do is we take a small step in the opposite direction. Like the gradient is basically the slope, right? In which direction the point is flowing. So we take a small step in the opposite direction because, well, we want to minimize it. And over here you can see in this plot, the red areas are the higher plots, the higher regions, the places where we don't want to be, and the darker purplish bluish regions are where we actually want to be, the minimum loss, the optimum weights rather. So over here, this is our global minima. This is where we want to reach. So we feed this network back, right? And we reach this global minima. So if I may move on, I'll make you understand this in this algorithm that we have. So what we do is initialize the weights randomly, at any point. We might use certain algorithms for that as well, but we'll talk about the initialization methods a bit later. And then we're going to loop this until convergence. What are we going to loop? No, we're going to find out the loss function, and then we're going to calculate the derivative, and then we're going to update the weights quite in this fashion, where our W new is going to be W old minus the eta times of our loss function's derivative, or the gradient. Right? This is basically gradient descent algorithm. We're going to calculate it for every single step. So when we're calculating for every single step, this is a special kind of gradient descent, known as stochastic gradient descent, where we're not calculating the loss for batches, but rather for individual entities. For individual y's, we're calculating the loss and the derivative. So this is our update rule, that y new is going to be the y old minus eta times our gradient. So now an obvious question that comes to the people watching this is, what is eta? Eta here is nothing, friends, but something called the learning rate, and that is something that we need to change. In a neural network, while training a neural network, the things that we need to change as an engineer, that actually is the job of an ML engineer, the things that we need to change as from the outside, the things that are not going to happen via the program or via the neural network will not do automatically, are known as hyperparameters. So over here, this learning rate is a hyperparameter that we need to optimize ourselves, right? So we'll get into choosing how to choose the optimum learning rate in a while. So moving on, we have this gradient descent. This is it in code. You can refer to my GitHub. I'll be posting it in the comment section when I'm done with the course. You can all just look at my GitHub and just understand what the code is for. So yeah, this is the code. And as I said, we propagated backwards. So what exactly do we do when we're propagating it backwards? We'll get into it. So what we're doing is we're taking the derivative, right? So when we're taking the derivative, we basically want our derivative to be a function of our inputs. But it's had a lot of transformations in the middle, right? So we've applied non-linearities to it. We've taken its weighted means. We've applied a softmax function in the end to get the probabilities of the end scenario. So what do? We take the derivative of the the y pred with respect to the weights of the previous layer, because the y pred is now a function of the previous layer, right? And we can easily use the chain rule to get back to y pred with respect to x, right? So over here what we're doing is, if we are to find out the derivative of y pred with respect to w2, we can find out the derivative with respect to y hat, and that the derivative of y hat with w2, right? This is the weight in the second layer, if you confuse what w2 is, and this is what our prediction is, and on that we've applied a softmax function to obtain our jw. If I've not mentioned softmax before, which I don't think I have, softmax is basically something which gives you the probability that what might be the outcome of that particular class. So this is basically what backpropagation is, how we are going to update the weights. So moving backwards, we have it in terms of x at the end. So we repeat this for every single weight, and then now you might have an idea of the amount of calculations that we we actually need to do to obtain the correct output. And we need to do this a lot of times, a lot of iteration, so that finally we can get a loss which is near to zero, or it's epsilon. So neural networks in practice, they have optimization. So I'll be waiting for a few questions if you have any right at this stage. Any questions, guys? Okay, then since I see no questions, I'll move forward then. Cool. Yeah. So, well, training neural networks is difficult because, frankly, say your weights are initialized at this peak sort of place and you need to reach this crevice. Well, you actually find a lot of minimas, right? A lot of local minimas before you reach the absolute global minima. So your network might think that it's reached the global minima, but it's actually not. It's reached a local one, and it's going to give you semi-par results, which is something which we don't need. So over here the concept of increasing your learning rate comes, because in essence, if you're going to talk about learning rate, I'll just give you an analogy. Learning rate is basically the amount of risk you're willing to take, right? The amount of risk you're willing to the larger your learning rate is, the larger is the amount of steps you're going to take. Alright, so the larger your learning rate, the more you're going to reach your global minima. There's more probability you're going to reach your global minima, but that's not always true. I mean, if you invest in a larger running rate, a larger running rate will require more computational power in certain cases where it might just overshoot the global minima. It'll overshoot the global minima, and then the minima will be in the opposite direction. It'll again overshoot the global minima, and then you have to spend a lot of resources in this oscillation around the minima. So we'll get to it, how we can reduce that. Alright, Mansi wants me to explain what softmax is. Well, Mansi, softmax is basically a function, like any other function. Okay, like you don't have that doubt. I'm confused. Like, never mind. I'll just explain softmax again. So, softmax is very similar to the non-linearities that I told you about before this, but it's not actually a non-linearity. It's just a function. What this function does is, suppose at the end layer you get values like 0.8 minus 0.5 and say 0.3, right? So over here in a probability distribution of sorts, you're not supposed to get negative values, but your network says that this has a negative value. So what it basically does is it's not going to take the sum of all these together and divide it so that you get the mean and and you can predict what the actual class is. Since we have a negative term here, it would be foolhardy to do so. This softmax function, you can go and you can Google what the softmax function actually is mathematically, but what it does in essence, it tells you what has the most probability. If you have a multi-class classification, applying the softmax function in the end will tell you which class has the highest probability. It is basically a probability estimator of sorts. So I hope I've cleared your doubt in that case, Mansi. So loss functions can be difficult to optimize. This is the learning rate, the eta that I was talking about. So setting the learning rate, right? A small learning rate converges slowly and gets stuck in a false minima. So if you're starting from this place, we're going to get the learning rate, if it's slow, we're going to be satisfied. Since this is more or less a low position for the network, it's more or less satisfied that yes, I've reached a minima and I'm happy with it. But if you were to take a larger learning rate, it would converge faster. Like, I won't say it would converge faster, it would take larger steps. I mean, it wouldn't have stopped here. It would have probably gone here and it would have seen a minima here, right? The gradient over here is to an extent still increasing and it's decreasing over here. So it'll take a step back, but the learning rate will again push it to take a step forward and it'll end up somewhere here. And you'll see that the gradient will push it to go in this direction where a global minima is. So it'll go in this direction. And the learning rate will again push it forward. So it'll go in this direction and it'll see that yes, the gradient, the global minima was in this direction. So it'll come back again, and in a sense, the learning rate will again push it towards this direction, and it'll then come back, it'll overshoot, and again come back, and that sort. A very high learning rate has its disadvantages, I'm sure, but that's what ML engineers are required to do. I mean, find the actual learning rate, the optimal learning rate of sorts. So learning rates overshoot, become unstable, and diverge. Yes, I've talked about this. So stable learning rates converge smoothly and avoid local minima. So yes, talked about this too. Try lots of different learning rates and see what works just right. Yes, that's true. We can do that. Yes, how to deal with this? Do something smarter. Design an adaptive learning rate that adapts to the landscape. Till now, we had talked about gradient descent as our learning function, right? That's what we were going to do. We're going to do backpropagation using the gradient descent algorithm and optimize our weights. So you would be very happy to know that there are algorithms which perform much better than stochastic gradient descent in a lot of real life scenarios. There are things like there are variations in gradient descent called momentum based gradient descent, which practically looks at the history of the steps that you've taken. I have extensive work on this in GitHub. You can just look at it later on. So as I was talking about momentum based, then we have Nesterov accelerated gradient descent or NAG descent. That again is for another session where I could take another session altogether on learning rates and learning algorithms. And then you have at learning rates, like just read through this. Learning rates are no longer fixed. I mean, you need not give a learning rate, or in case of stochastic gradient descent, you need to specify a learning rate, right? In case of a learning function, or in case of a learning function like Adam or Adagrad, I will get to these. These are really complicated learning functions. The learning rate adapts on its own. It updates on its own to reach the correct position. Yeah, so it can be made larger or smaller depending on how large the gradient is, how fast the learning is happening, the size of particular weights. So basically the history term that I talked about is how fast the learning is happening. So momentum-based gradient descent and Nesterov-accelerated make the decisions on how fast it's learning. How large the gradient is, the same principle. So we have, this SGD is stochastic gradient descent. We have Adam, we have Ada delta, we have Ada grad, we have RMS prop. So these are very different, it might seem a lot to take in, but basically the software packages, the TensorFlow implementation, you can look at this and understand very easily what it's all about. So, alright, I'll have to speed up my session. My time has been exceeded. So you can replace, this is in code, I'll skip the code. Yeah, now we can do gradient descent for individual elements, like stochastic gradient descent, or we can do it in a sort of mini batch gradient descent, right? What mini batch gradient descent does is it finds out the loss for batches, right? So you need not perform the same computation for a single element. You can find it out for a very a 32 or 64 batches of 32 or 64 or 128. We have these in powers of 2 because while putting it on a GPU, a GPU optimizes it to run in powers of 2. So that's why we put it like that, so it can be more parallelized and we're not wasting any resources. So the stochastic gradient descent can be indeed computationally intensive to compute, right? So we're done with this. Yeah. Mini batch gradient descent, it's faster to compute and a much better estimate of the 2 gradient, right? So it's talking about pick a batch of B data points and find it out, then update the weights for that batch. It's fast to compute and a much better estimate. This is called a mini batch gradient descent. So mini batches while training, we have smoother convergence and it allows for larger learning rates. Can parallelize computation, achieve significant speed increase on GPUs, as I was talking about. I mean, you should make your batches in powers of 2 because the GPUs are optimized for that. Yeah. Now we're talking about overfitting, right? So what exactly is overfitting? Overfitting, guys, is, if you look at this diagram over here, this is the set of data that I have. And this is when the model has not been trained enough. I mean, it is doing more or less equal job at classifying the upper points and the lower points, or if you might say computing the function. But over here, you'll see it's not learning a lot. But in the middle place, you'll see an ideal fit. I mean, this is basically what the function was actually supposed to be. But if you train it more, the function you're trying to estimate actually goes towards overfitting. When it becomes too complex, higher dimensions, it takes in, you'll see that this is one-dimensional, this is two-dimensional, and this is a lot of dimensions, like 1, 2, 3, 4, 5, 6, 7 if I'm not wrong. It's a 7-dimensional function. So, well, that's not what we want, because if we are to give test data to this, it will not lie on this function, and it'll probably because this is going to be a waste of resources as well, right? We're going to be computing a lot to reach this place. So overfitting is something which we don't actually need, because we're going to be wasting a lot of resources and not reaching our target. So how do we get rid of overfitting? This is something called regularization. Okay, regularization is a technique that constrains our optimization problems to discourage complex models. So I have a write-up on regularization techniques on towards data science. I'll put in the link as well. So if you really want some insights into what regularization is and what it does, you can just go there and have a look. It's in pretty simple language. So type 1 regularization is dropout. Dropout is where we randomly set some activations to 0, or in simpler words, what we do is we make certain neurons dead, right? So we have 1, 2, 3, 4 over here, and like 1, 1, 1, 2, 1, 3, and 1, 4. We have 2, 1, 2, 2, 2, 3, and 2, 4. We'll consider these neurons to be dead, right? We'll not pass any information through them during our forward propagation, and similarly during our backward propagation, these ones are not going to get updated. So what this does is basically it enables the neurons to become self-sufficient of sorts. It can perform in the absence of other neurons as well. So what this makes our model or neural network is it makes it more robust. It makes it, more generalized. That is our primary aim here, to get the general outcome, not a very detailed or more overfitted outcome or result. We don't want that. So you can perform dropouts like this, and then we have early stopping, right? So what exactly is early stopping? We can stop training before we have a chance to overfit. For that early stopping, we need something known as validation data. They've mentioned it to be a testing data here, but I like to call it a validation data because I consider there to be three kinds of data: a training data, a validation data, and a testing data. So we train the model on the training data, and we perform certain optimizations using the validation data. And when the model is trained, when we're not going to perform anything on it, we are going to use the testing data to finally get what is our accuracy on the model of the model on data it's previously unseen, right? So this is early stopping. You stop training before you have a chance to overfit. Yeah, over here the validation loss, or the testing loss in this case, is also decreasing along with the training loss. But then what will happen? It starts increasing. I mean, this is definitely a case where you're seeing a model overfit itself. I mean, where it's not performing good to unseen data, but it's rather memorizing the data that it has been given during training. So over here, the training loss has been driven to 0 nearly, and the testing loss or the testing error is pretty high. So what do you think is the stage where we need to apply early stopping? I mean, let's just name this as 1, 2, 3, 4, 5, and 6. Where do you think our model needed to stop? I'll be looking in the comments for your answers. Any answers? Where do you think our model should stop learning? Correct. 4. 4 is the correct answer. That is exactly where we should stop learning. We should stop training here, because this is the place where we have an optimum solution, right? Stop training before we have a chance to overfit. Correct. Alright, so with that I think we reached the end of the slides. Yeah. Core foundation review. The structure, perceptrons are structural building blocks. We have nonlinear activation functions because, well, we need nonlinearities in data so that we can get a proper estimation of the classification that we are about to do. We stack perceptrons to form neural networks or multi-layer perceptrons. We optimize them through backpropagation. I mean, that involves a lot of mathematics behind it. I've just gone over very roughly what it is. And what we're going to be training using adaptive learning, batching, and we've talked about regularization a bit. So these are indeed the best practices. And now I'm going to tell you a bit about what to use where, right? So what are the hyperparameters that we have? So, if you have any doubts on deep learning or what you should do on what convolution, unfortunately time doesn't permit us to talk about convolutional neural networks and recurrent neural networks or something called generative adversarial networks. There's a lot to deep learning. I'm not even scratched the surface. So if you have any doubts, if you want to know more, please feel free to contact me on LinkedIn. I'll be giving that link out as well after I'm done with the session. So kind of summarizing, the hyperparameters that we need to understand is, in the network architecture domain, we have the number of layers that we need to give and the number of neurons in each layer that we need to specify, right? So these are hyperparameters which, if me and you as people don't really set, because a change in the number of neurons or number of layers can lead to drastic changes in your learning rates and all that. We have researchers who've created models in this sense. We just tweak it a bit, change the learning rates, or maybe add our own layers in the end so that it suits our problem. This technique is known as transfer learning, if you've heard of it. Again, I have well documented code of transfer learning in my GitHub repository on PyTorch and TensorFlow, both of them, right? So then another hyperparameter which we need to set is what activation function should we use. We have, as we talked about, the sigmoid, hyperbolic tangent or tan H. We have ReLU. We also have something known as leaky ReLU, which is basically all the negatives of ReLU, it takes it away. And ReLU is basically one of those activation functions which is most widely used, if I'm to say that, and that's probably it. So I'll tell you where to, if you're watching this video at your home, then I'd suggest you write these down. So you should use the tan H activation functions when you're working with recurrent neural networks or RNNs. You should use the ReLU when you're working with convolutional neural networks or even dense neural networks or deep neural networks in that sense. And you should use the leaky ReLU. I'm not talked about the leaky ReLU extensively, but you can Google it. It's pretty simple to understand. ReLU and leaky ReLU don't need a very deep understanding of mathematics. It's pretty simple to understand. So leaky ReLU, in case you'll use it in convolutional neural networks as well. In case anyone didn't catch it, tan H for RNNs, ReLU for CNNs and even feed-forward networks, and leaky ReLU for CNNs. Then you have your regularization techniques. We talked about early stopping. We talked about dropout, but there are a lot of other things known as L2 regularization. We have data set augmentation. Data set augmentation is a really fun thing. So I'd suggest you go to my repo and find out that augmentation in the TensorFlow files. It's really interesting. It really makes you wonder where deep learning has gone today. And batch normalization. Well, batch normalization is another thing that, these regularization techniques as I was talking about, I'll share the link of my post on Towards Data Science. It's been explained in pretty simple ways there. So I'd suggest you go and look there. So for the learning algorithms, we have our vanilla gradient descent, we have a momentum based gradient descent, we have our Nesterov accelerated, Adagrad, Adam, RMS prop, all of these. Then we have the strategies that we need to apply. We can batch the data, we can take the entire data to be one batch. We can take mini batches in powers of 2 so that our accuracy is high and our training time is low. And then we can also have stochastic gradient descent for small tasks, because that's actually very accurate when you're performing small tasks. So that's there. Okay, so this is the end of the session. So right now I'll just be sharing my repo links and my LinkedIn account and all that. So you can just go there and contact me if you have any doubts, or if you have any doubts right now, you can also put it in the comments right now. I can address them. So just we'll be ending the session shortly. So any doubts is really welcome. I'll be sharing the links. This one is the thing I've posted is my LinkedIn profile. So any doubts you have, feel free to contact me. Right. And this is the link where you can go and read more about regularization techniques. And talking about if you really want to be if you want to undergo the journey as I have, I'll talk about my inspirations that I had. I'm a student from VIT University in Vellore, and over there we have this chapter called Witmas. So I was interested in cybersecurity, and I wanted also to do machine learning and stuff. So in Witmas, the mentors that I had there were amazing. I mean, they just told me to go on this path of deep learning and machine learning so that I could understand this and implement my knowledge on these things in cybersecurity fields. And deep learning, you can apply it anywhere actually. So in Witmas, I had a lot of guidance, support from the mentor that I had, and it was really an amazing experience. So you could just, if anyone of you is in VIT, you could just come and talk to me, and we could probably even share the same mentor. So just putting it out there for people. And this is the GitHub repository link of mine, where you can go and find out whatever I've talked and more. You'll have a lot of files pertaining to convolutional neural networks, recurrent neural networks, which I haven't explained in this short course or short webinar, if you might say. So any doubts on that, feel free to contact me, right? So I'll be ending the session now. So now would be a really good time for you to tell me if you have any doubts of sorts. Any doubts, guys? Okay then, since I see no doubts, then very well then. Thank you. It was an amazing experience. This was my first time doing something like this, and thoroughly enjoyed it. Thank you all for being here, and hope to see you again. Bye bye.